Welcome back to our Advanced Thermodynamics series. Today, we are undertaking a truly comprehensive 7.5-minute deep dive into the Brayton cycle. This is the foundational thermodynamic engine cycle that powers modern aviation and industrial electricity generation worldwide. In this extended lesson, we will break down the physical components, transition from open to closed system analysis, map the 4 distinct processes on our diagrams, perform a rigorous derivation of the efficiency equations, and examine real-world refinements. The Brayton cycle is fundamental to understanding how we produce power from gas turbines. Whether it's in a jet engine propelling an aircraft across the Atlantic or a stationary turbine in a power plant, the core principles of compression, combustion, and expansion remain the same. Today we look deep into the why behind the design. As we see here, the physical scale of these systems is immense. A typical gas turbine operates as an open system where fresh air is drawn into the compressor, mixed with fuel in the combustion chamber, and then expanded through the turbine to generate work before being exhausted. This continuous flow is what sets it apart from reciprocating cycles. To simplify our engineering analysis, we idealize this as a closed cycle using the air standard assumptions. We treat the working fluid as air with constant properties throughout and replace the complex combustion processes with heat exchangers. To simplify our engineering analysis, we idealize this as a closed cycle using the air standard assumptions. We treat the working fluid as air with constant properties throughout and replace the complex combustion and exhaust processes with constant pressure heat exchangers. This makes the mathematics tractable without losing the core physics. Visualizing these states on both PV and TS diagrams reveals the nature of the work done. On the PV plot, we see the volume changes during compression and expansion, while the TS plot clearly shows our energy addition and rejection paths between our constant pressure isobars. This dual view is critical for total system analysis and troubleshooting. The cycle begins with isentropic compression from state 1 to 2. In an ideal world, this process happens with no change in entropy, meaning no internal friction or heat loss. We are essentially concentrating the energy of the air, preparing it for the massive heat addition phase that follows. Next, we move to constant pressure heat addition. In our ideal model, this is the heat exchanger phase, where we raise the air to its maximum cycle temperature at state 3. This is where we put the energy into the system, transforming cool air into a high enthalpy gas ready to do massive work in the turbine. From state 3, the high energy gas undergoes isentropic expansion through the turbine down to state 4. This is our power stroke. The work produced here must be sufficient to drive the compressor and still provide enough excess power to turn a generator or drive a high bypass fan. This net work is our ultimate goal. Finally, heat is rejected at constant pressure from state 4 to return the air to state 1. This completes the loop. In an open system, this happens as we exhaust hot gases to the atmosphere and take in fresh, cool air, essentially using the entire world as our heat sink for the cycle. This phase is crucial for resetting the fluid. Thermal efficiency is the most critical metric for any power cycle. It's defined as the net work output divided by the total heat input. In a Brayton cycle, we analyze this by looking at the enthalpy changes across each of our 4 components, assuming cold air standard conditions for our mathematical derivation. To find the efficiency, we perform an energy balance. We subtract the work required by the compressor from the work produced by the turbine. Under the air standard assumption, these enthalpy differences can be expressed simply as the product of specific heat and temperature change, leading us to a ratio of delta T values. Using the isentropic relations for pressure and temperature, we arrive at our final, elegant result. The efficiency equals 1 minus 1 over the pressure ratio raised to the power of K minus 1 over K. This formula is the guiding light for all modern gas turbine design, material selection, and optimization strategies. The takeaway is clear. Efficiency increases as the pressure ratio across the compressor increases. This is why modern engineering pushes for higher and higher compression. which in turn requires advanced, high-temperature materials and complex cooling to withstand the resulting conditions without melting the turbine blades. As we see on this chart, the gains are significant early on, but we eventually hit diminishing returns and harsh physical limits. Specifically, the maximum turbine inlet temperature at state 3 is bounded by the melting point of our materials, a frontier we are constantly pushing with advanced ceramic coatings. To exceed these ideal limits, engineers use refinements like regeneration to reclaim exhaust heat and preheat the air before it enters the combustion chamber. We also use multi-stage compression with intercooling to reduce the work input required by the compressor, significantly boosting the net power output. In a regenerative cycle, the high-temperature exhaust at state 4 is used to heat the air, leaving the compressor at state 2. This reduces the amount of fuel we need to reach the turbine inlet temperature at state 3, directly increasing the thermal efficiency of the entire system. Looking forward, the Brayton cycle is evolving with hydrogen fuel integration for zero carbon emissions and additive manufacturing for internal cooling channels. We are even developing ceramic matrix composites that can handle temperatures far beyond what was possible just a decade ago, paving the way for next-gen turbines. To summarize, the Brayton cycle is defined by its 4 core components and its alternating processes of isentropic work and isobaric heat transfer. Its performance is fundamentally linked to the pressure ratio and the material limits we face in our quest for higher efficiency and sustainable power. Before we conclude, I'd like to remind you that in our next session, we will explore engine propulsion, thermal, and overall efficiency. This involves a rigorous control volume analysis using the conservation laws of mass, momentum, and energy, concepts I discuss in detail in my upcoming book, The Engineering of Life. As shown here, the control volume of the engine allows us to track every joule of energy and every kilogram of air as it passes through the system, ensuring our designs meet the highest standards of efficiency and performance. I look forward to continuing this journey with you. Lesson adjourned.